Okay, thank you, Christina, for the introduction. So I'm Leah Morabito. I'm at Durham University, and for those of you who know me, know that I've been working for like the last decade on LOFAR, and in particular, high-resolution imaging with LOFAR. But I've been asked to talk to you today about the distant universe, so I will sneak in a little bit of high-resolution LOFAR at the end, but this will be a broader talk looking towards the high redshift universe. So Linder talked on Tuesday about the distant universe part 1, so galaxy formation and baryons through cosmic time. And today we're going to focus on how we trace the large-scale structure in which galaxies live. So this talk is divided into 3 parts. We'll first cover tracing the evolution of large-scale environments, and then we'll talk about the formation and evolution of the most massive and luminous galaxies in our universe. And that's not necessarily looking at them when they are the most massive and luminous, but also the progenitors of the most massive and luminous galaxies. And then we'll finish up with learning from Pathfinder science. So Tyler kind of like stole the thunder here for people who have posters because he told you to start taking them down. I will refer to posters throughout the talk because I am not a cosmologist. I'm not an expert on all of the topics I'm going to cover. So I have referenced posters, and so hopefully you can sneak in a look at them if you haven't already during the lunch break. Okay, so starting out by tracing the evolution of large-scale environments. So when the SKA was first proposed, it was first called the hydrogen array when in its initial conception. And Peter Wilkinson said that a volume of the Encyclopedia of the Universe is written in 21 centimeter typescript. So we can trace the large-scale structure by looking at the distribution of neutral hydrogen. And Christine and Eric talked yesterday about detecting individual galaxies with H1. So looking towards detecting individual galaxies out to about redshift 2 is what Christine said yesterday. So how do we push this further towards cosmic dawn? Well, if an individual galaxy is too faint to detect, then maybe what you can do is you can start looking at concentrations of galaxies or where you have concentrations of H1. And if your beam size is about the same size as the concentration of H1 that you're looking at, you might have a very good chance of detecting it. So this is, for example, maybe a higher redshift galaxy cluster or protocluster where you have a lot of H1 concentrated in one region that's about the size of your beam, and that increases your chances of detecting this. So then if you have these distributed across the sky, then you can start doing a survey, and you get what we call an intensity map. So for those of you who are not familiar with this, intensity mapping will show you the distribution of the H1, but not on individual galaxy scales. And so on the right-hand side of the slide here, you can see 2 columns. The left-hand side is the H1 temperature, and the right-hand side is the H1 fraction. So these are simulations, just to give you an idea of what we might see. And you can see the redshifts for them. At the top, you start at redshift 14, and the bottom panel goes down to redshift 7. So you can immediately see this is a kind of SKA low science, right? Because you're not going to reach the 21 centimeter line at these redshifts with the ngVLA. Okay, so people have been working on this in the community for a while. So doing intensity mapping for the epoch of reionization, and have produced some upper limits. So what I'm going to show you are not intensity maps. They're going to be, I'm going to show you power spectra. So you take your intensity map, and then you can find the power spectrum of H1. This does require very careful foreground subtraction and exclusion when you're doing intensity mapping, which is a whole topic in and of itself that I'm not going to go into, but there is a poster on it, and there's also some references on the slide if you're interested. There's been a lot of work done on trying to remove foregrounds from the EOR signal. But people have started to publish upper limits. So here we see upper limits from LOFAR, GMRT, and MWA. So SKA and ngVLA, or SKA Pathfinders or precursors. And so the redshifts are listed in the upper left-hand corner of each plot. So LOFAR at redshift 9, GMRT about 8.6, and MWA around 7. There's also a couple posters on this. So you can see here that you have points, which are the upper limits, and then all of the plots have lines which show you kind of like the estimated noise or the thermal noise of the telescopes. So really trying to get down, beating down the sensitivity, and this is really where the SKA will come in, providing more sensitivity to be able to push these points lower towards the noise. I won't cover it here, but just note that if you don't have an interferometer, if you just have a single element radio telescope. You can also do global experiments, and so in that case, you're not doing intensity mapping, you don't get the 2D spatial distribution of H1, but if you have a wide frequency band, you can get the H1 temperature, the average H1 temperature for the sky, as a function of redshift. And there's a poster on that. We already saw the Sparkler talk for that. Okay, so that's the gas, but what about the galaxies? So one of the things you can do is you can look at angular correlations of galaxies to understand the distribution of the large-scale structure in the universe. So angular correlations, for those of you who don't know about this, is very, very simply, you're comparing the number of galaxies in a solid angle to what you would get if those galaxies were distributed randomly on the sky. So there's a lot more details to this, but this is just kind of the basic concept. So if you have a solid angle, as depicted by this box, the purple box in the middle there, if that's your random distribution, then you take that same solid angle in your real survey and you look to see if you have perhaps excess galaxies in there, so excess clustering, or perhaps a deficit of clustering. And so you can do this for a large number of solid angles, and so you can get the angular correlations, so how clustered your galaxies are on different scales on the sky. So here's showing you what you can then do with that. So you can then kind of relate your angular clustering to the dark matter, the underlying dark matter halo. This is called galaxy bias, where you take your angular clustering of galaxies and relate it to the dark matter. And so this figure is from a GMRT survey of LASN1. It shows you galaxy bias versus redshift. And so the lines on there are the models. So these are your models of what you think is happening with the dark matter in the universe, and then you can see the points on there. And so this is just a single field, but if you start doing this for the entire sky, then you can get a better idea of what's going on in much larger populations. Okay, so those are two different ways to kind of trace the large-scale structure. So you've got H1 tracing gas, you have galaxies tracing concentrations of stars, but you can actually combine those together. So you can combine intensity mapping and clustering. And this is a really flexible way to kind of look for correlations between different structures in the universe. And here's just two examples that are combining intensity mapping and clustering in different ways. So the top example there, the intensity map that's used is Meerkat H1 intensity map. So this is at low redshift, so looking at H1 at low redshift, and then the galaxies are from WiggleZ. And so this is looking at the power of the correlation between H1 and galaxies as a function of the scales on the sky. The bottom example here shows you the intensity map that was used is the CMB lensing convergence, and the galaxies are from the LOFAR 2-meter sky survey. So the bit of data that's used, that's in bold, that's the radio. And so this shows you the flexibility of this method of combining intensity mapping and clustering, because you can take your galaxies from your radio survey, or you can do a radio intensity mapping, and you can cross-match it with multi-wavelength things. And so this is something where you could potentially envision that you do line intensity mapping maybe for CO with ngVLA, and use SKA radio continuum surveys as the galaxies. So a really flexible and potentially very exciting way to trace structure. Okay, that's all I'm going to kind of cover for this first section, but if you get a chance, there are posters with more on cosmology and large-scale environments. So looking at cosmological studies with the LOFAR 2-meter sky survey, and also a couple posters looking at the magnetized cosmic web. Jeremy Darling also gave a talk on the cosmic dipole. There's a poster on it as well. So I highly recommend you go in and check those out. Okay, so moving on to the second part, the formation and evolution of the most massive and luminous galaxies. So here we're really talking about radio continuum surveys. And the most basic thing that you can do with a radio continuum survey is you can do source counts. So Alison Matthews, who gave a talk on Tuesday, this is from some of her early work, and I really like this example because it's combining precursors to both the ngVLA and the SKA, so using VLA and Meerkat, combining the NVSS and deep 2 fields to get source counts across a very large range of flux densities. So this is the most basic thing you can do, and as Alison described on Tuesday, you can start to compare your source counts with models of galaxy formation and evolution and really understand the bright and the faint populations. So you can also, I think, with the SK and the ngVLA, one thing that will be really powerful is start looking for differences between frequencies, but the SK and the ngVLA will have a large overlap of frequency coverage, so you'll be able to calibrate your source counts and the overlap, and then look at the source counts at lower frequencies and higher frequencies to identify if there's maybe different radio emission mechanisms that are impacting your source counts in those regimes. So we'll come back to source counts towards the end of the talk. Okay, if you want to do more with your radio survey, then you need multi-wavelength information to add value to it. And the kind of Pathfinder surveys towards the SK are really doing this very well, producing catalogs that have this value-added information. And here are just several examples. So Cosmos with the VLA, the LOTS deep fields with LOFAR, and Mighty with Meerkat. And so you can see we're starting to push out towards higher redshifts, so towards cosmic dawn, although we're reaching about maybe redshifts of 5 to 6 with these kind of like mid-area surveys. To really push towards cosmic dawn and find those high redshift galaxies, we really need to go to wide area surveys to find rare sources, and there are a couple posters on wider area radio surveys here at the conference. So we do know about radio galaxies sort of towards the epoch of reionization. Radio surveys have been a very successful method actually for finding, since the late 1970s, for finding high redshift sources, thanks to this observed correlation between the radio spectral index and redshift that you see on the right here. And so that purple dashed line is the definition of ultra-steep spectrum sources. So anything above that is ultra-steep spectrum. And you can see that if something is ultra-steep, it has a higher chance of being at high redshift than something that's not ultra-steep. And so here's an example of 2 sources that were found that are both at high redshift, above redshift of 5, that were found using this were selected because they had ultra-steep spectra, and then you follow up with spectroscopy, which is expensive, but then you're doing it only for a very small candidate number of sources. But this gives you kind of a biased view of the high redshift population, because again, this is an empirically observed correlation, and so we don't know if this is actually driven by something physical. There's been some work that shows that maybe it's not, that it's observational. But you can expand your selection of high redshift sources with the kind of new radio surveys that have this multi-wavelength value-added information. So Anik will talk about this later, people have developed methods using combining radio detections with dropouts in photometric bands. And you can see that these high redshift sources, and now we're pushing out to a redshift of 7, are not ultra-steep spectrum. There's maybe 2 that would qualify for that definition. So see Anik's talk about this later this afternoon. But why do we care about finding radio galaxies in the epoch of reionization? Other than just studying that high redshift population, which are already massive and luminous galaxies, one thing you can do is you can go back to the H1 and start looking at the H1 distribution along the line of sight towards these galaxies. So this is a simulation of a galaxy at a redshift 8 and essentially the idea here is that if you find a bright enough background radio source, then you can see a 21 centimeter forest, kind of like the Lyman alpha forest you would see in optical, of the intervening gas that's absorbing the H1. But this requires you to be sort of in the epoch of reionization, so you have this gas in front to actually do the absorption. And if you can see, here's another example of a galaxy at a redshift of 10, and here it's much clearer here that you can start to see the absorption from the neutral gas in front of this galaxy. So this is at redshift 10, but there has been recent work that's shown evidence that the end of reionization may be as late as around redshift 5, and so that's helpful. And so hopefully within the next few years, we'll actually be able to see something that's not a simulation to show us something about the H1 along the line of sight towards a very distant galaxy. Okay, so in the last 10 minutes or so, I just want to introduce you to some more Pathfinder science that you can do with radio continuum surveys. So going back to source counts, let's first think about what we will see with the SKA and ngVLA and compare that with where we are now. So these are two semi-analytic models. And so again, Allison introduced this idea that you can take models of galaxy evolution and you can forward model them into source counts and then compare them with your observations. So there's a couple different models. So SCADS on the left and T-Rex on the right. And they have their pros and cons. So SCADS is nice because it's broken into different populations, but then again, not all of the populations do very well at reproducing the observations that we have. T-Rex has better overall agreement with observations, but it isn't broken down into the populations. And so I think this is something that we can already start to work on with the data that we have now up towards the ngVLA and the SKA. So to give you an idea of where we are now with some of the surveys I've shown you, the LOTS deep fields and then the mighty early science and the cosmos field, this is kind of where we sit. And this has all been scaled to the same frequency. And so you can see that we're starting to shift from this bump on the right, which is the radio loud population, into the bump on the left, which is the radio quiet population. And so really starting to understand more of what we see in the radio sky. So where will we get with SKA and ngVLA? So with 1 hour of observation time, with either the ngVLA or SK1, you kind of improve by almost an order of magnitude. And so we'll really start to probe down even further into this radio faint population. Yes? Okay. All right, so let's first talk a little bit about new results with on radio loud HN. And so to give you an idea of how we've improved in the last few years in radio surveys, this is a figure from the LOTS data release 1. So this is showing you power versus size, which is a figure that Pallavi showed on Tuesday. And you can see the pink dots are 3CRR, and then the LOTS data release 1, which is only 325,000 galaxies, and now we have 4 million in data release 2. You can see we're really filling out this PD diagram with the colored points in the background. And from this, we've already had a couple of surprises. So Rick Perley introduced the idea of FR1s and FR2s yesterday. And in the 90s, we thought that in this top plot here, this is radio luminosity versus stellar mass. We kind of thought that the FR2s were above what is this black line here, and that the FR1s were below it. And now we're finding with LOFAR that that's not the case at all. These two populations have a huge overlap. And so that's really a challenge for our understanding of how those jets are launched and what kind of accretion modes they may or may not have. So with the MIGHTY survey, we also see that there's a very large overlap in radio galaxies with different accretion modes. So high excitation radio galaxies are kind of thought to have cold mode accretion. So there's cold gas, a standard accretion disk, and low excitation radio galaxies, which are thought to accrete stochastically from hot gas. We had seen that there was a division in their accretion rates, but now with our deeper radio surveys, we're seeing that there's a much, much larger overlap in the Eddington rates than we previously thought. So this is really already challenging what we know about this radio loud population, and we'll just discover more as we go down in sensitivity with the ngVLA and the SKA. So I really like this plot, which is from an upcoming paper by Nico Yerlin, because it's the life cycle of radio galaxies in one plot. So Pallavi introduced, restarted and young AGN on Tuesday, and this is everything in a single plot. So it's very complicated, so let me walk you through it. So the green contours there are LOFAR, are from LOFAR at 150 megahertz at 18 arcsecond resolution. The blue is from LOFAR at 150 megahertz with 6 arcsecond resolution. And then we have some contributions from the VLA. So the first survey at 5 arcsecond resolution, VLS at 2.5 arcsecond, and I'll talk about the purple ones in a minute. But the thing to note about this is that the very large scale fluffy stuff, right, that's in the green contours, that's all very old. That's the old electron population. So that's the remnant of a radio galaxy. And it's turned off. We don't see it at higher frequencies. You don't see it, for example, with the first, which has a similar resolution to LOFAR at 6 arcseconds. And so this radioplasma has aged and you no longer detect it at low frequencies. And this is something where the SK and ngVLA, the wideband frequency coverage, will really allow you to start aging the spectral plasma, the radioplasma in these sources to get spectral ages and to be able to really study the life cycle of radio galaxies even in just one galaxy. Okay, so the LOFAR 6 arcsecond resolution, and most of the LOFAR results you've probably heard of have come from something like LOTS, which uses just the Dutch stations in the whole array. But if you expand out to using the entire array, you can get 0.25 arcsecond resolution, which is the inset in this plot here, which shows a restarted jet. So this jet, this is not related to the older structure that you see in the green and the blue. This is a completely new jet because this radio galaxy has turned back on. And it's only possible to see this now with using the full international array. But of course, the ngVLA will be able to get this kind of resolution routinely on these kinds of galaxies. So see also the posters by Christina and Amelia for more information on young radio galaxies. Okay, so in the last few minutes, I just want to show you something really cool you can do with LOFAR at sub-arcsecond resolution. So we can really start to understand the radio quiet population with what I call LOFAR VLBI. So that's using the full array of LOFAR rather than just the Dutch stations. So this figure is reproduced from a paper by Jim Condon in 1992. On the y-axis is flux density per solid angle, and on the x-axis is frequency. The dashed lines on the plot are lines of constant brightness temperature. And what you can do is you can say, okay, if I have star formation in my galaxy, what is the kind of limiting flux density per solid angle that can produce? And that's this line here. So anything under the shaded region, it's the radio emission that you see is totally consistent with star formation. But if anything lies above that line, then you can identify that as an AGN. So historically, people have used this to identify AGN at about a gigahertz frequency. You need to get down to the flux density per solid angle, so per beam. To identify AGN, you need to go to VLBI instruments like the VLBA or the EVN. But at LOFAR, you can do this with the 0.3 arcsecond resolution, because you can see the limit for star formation is frequency dependent. So with LOFAR at 6 arcseconds, you cannot do this, right? You just have this blob, and the flux density per solid angle doesn't tell you anything about it. But as soon as you go to LOFAR VLBI, you can start to identify AGN at this frequency with this resolution. And so that's what we've done for the Lachman hole. So there's a very, very nice Nature Astronomy paper out last year with a 7 billion pixel image of the Lachman hole at 0.3 arcsecond resolution, 5.5 square degrees of field of view. And with this, we identified 940 AGN using brightness temperature. That's 160 new identifications. And one of the interesting things that we're finding is that actually a significant fraction of the radio quiet AGN and star-forming galaxies have high brightness temperature cores. And that implies that they're composite sources. And so this is really, I think, exciting to understand the radio quiet population. And if you're interested in either star formation or AGN, this is going to be interesting for you. So just to note that the ngVLA with its long baselines should be able to do similar kinds of things at the higher frequencies. So with this kind of information that we're learning from the radio surveys, we can start preparing also for the SK and the ngVLA by understanding our models and observations better. So for the radio loud population, Nicole Thomas, who's a postdoc at Durham, is working on comparing radio galaxies in the SIMBA simulation with observations and trying to figure out where we can improve our simulations. But with the separation of AGN and star formation, you can do with the LOFAR VLBI brightness temperature identification of AGN, you can start doing this comparison for physical processes rather than populations of galaxies, which is really exciting. So this plot here on the right, please take with a grain of salt, caution, caution. It's a very preliminary, but is very exciting for helping improve our understanding our theoretical understanding of the radio population. Okay, so in the last minute, I'll just pull it all together. So I hope I've shown you that the multi-radio wavelength coverage of SK and ngVLA will provide lots of opportunities to understand the systematics in the area where we have overlap between the frequencies, but also then to provide full radio SED coverage. There's a lot of complementary science that you can do with these two telescopes, but I will just note that like many of the results in the talk and many of the results we've seen in this week, that this is just a part of the larger picture, that multi-wavelength information will really be critical to put the radio in context. So Christina's on the stage, so I will just leave you up with my take-home message, which is basically what I've just said, and happy to take any questions.
Okay, any questions in the room? How about on Slack? Oh, I've got a couple. In the back? Whoever gets the mic first.
Yeah, so you're showing this thing with the Lyman alpha forest equivalent?
Yeah.
Is there any evidence for high redshift radio loud AGN that could be used to do this backlighting?
I'm going to refer you to Anik's talk.
Okay.
Yeah.
I was just interested in talking about intensity mapping compared to galaxy catalogs.
Yeah.
So I just wondered if there's some interesting new statistical thing being done. Maybe you could just point me to a paper and I'll...
So I will point you to Catherine Hale, who should be on Slack, because that's not my area of expertise, but I think she's been on Slack this week. She's participating remotely, and she should be able to help answer your questions.
I'll look on Slack. Thanks.
Yeah.
So you mentioned the multi-wavelength context. Thinking about the particular facilities that are coming online or maybe aren't delivering what they're supposed to deliver, like your Rosita, what's going to be sort of the critical path for the multi-wavelength perspective to put this all together?
I think that the surveys exist, right? So I mean, you can think about like LSST or Foremost and Moons, and I mean, in the northern hemisphere, like we have Weave LOFAR going to get spectra for things. So I think the surveys exist, and I think what's really going to be crucial is how we tie that information in with the radio. So surveys like LOFAR 2-meter sky survey have been very successful because they provide not just a radio catalog, but then a radio catalog with the value-added information. And I think that's really crucial for broadening out the number of people who can use the data, because if you just hand a radio catalog to a non-radio person, they're going to say, well, okay, what do I do with this? And they're not going to be able to fully exploit the data. But if you can hand a radio catalog and say, this is your FR2 galaxy, and this is its host galaxy, and this is its redshift, then you can really start to enable science for a larger number of people. And I think that pulling it all together, which is hopefully something we will do at the SK regional centers, is really what will be crucial to really fully exploit the data.
Sorry, I was hesitating until the last minute whether I should ask this question or not, but I decided to ask because the question is very naive, but I'm just wondering, recent JWST galaxies like the redshift, like the 7, 8, 9, 10, people talked about the spatial clustering. So those UV selected galaxies somehow tends to be clustered around somewhere in that high redshift epoch. But you also mentioned the possibility of the intensity mapping to actually characterize the gas distribution, right? How feasible or plausible do you think you could actually relate the distribution of galaxies at that high redshift at the gas distribution inferred from the intensity mapping?
Okay, so again, I'm not an expert in this area, but from my understanding is that to do these kinds of relations, you'll need large areas of sky, because you're looking at things like power spectra, right? So where your things are distributed on a large, like statistically on a large area of sky. So if you're looking at like individual galaxies, I'm not sure that that's really possible. But again, I would refer you to the Slack to perhaps ask that question in the Friday morning talk channel, and hopefully one of my collaborators can pick that up.
Thank you.
All right, we'll continue the discussion on Slack. Let's thank Leah again.